Hi, I'm Robert Kollman. I'm a Senior Applications Manager at Texas Instruments. Welcome to Power Tips. Welcome to Power Tips 3 and 4. In this Power Tip, we will discuss damping a filter. So the reason we're interested in damping filters is because many times we can set up an oscillation in the power supply with an undamped filter. This happens when your input filter resonates and creates a high impedance that the power supply has for a source. That can cause the power supply to oscillate. Now, here's the actual explanation behind it. On this curve, we have plotted input voltage and input current in a power supply. And so as the input voltage goes down, the power supply current goes up. That's because the power supply tries to regulate for a constant output power, and the losses in the power supply are typically not a large portion of the input power. So we get a curve that actually does this, and as you notice, the slope of that line is negative. And you can go through the math and calculate the fact that the slope of the line is equal to the voltage divided by the current with a negative sign on it. And it's pretty simple. So basically the lowest input impedance to your power supply happens when the current is the highest and when the voltage is the lowest. So that's over here on this portion of the curve. And that's what you have to consider when you're designing your damping for your input filter. So what I've drawn here is I've drawn three different impedances. The curve here in the purple line is the impedance of an inductor versus frequency. It simply goes up. The curve here in the dark blue line is the impedance of your filter capacitor, and as the frequency goes up, its impedance goes down. And the third curve is the output impedance of this filter. And what you can see at low frequencies, you see the very low impedance of the input filter capacitor. Very high frequency, you see the capacitive reactance of the filter. And you see in the middle there that the impedance goes quite high. What happens is the capacitive reactances equal each other, but they have opposite signs. And when you do the math, you get a positive and negative that gives you a zero in the denominator and gives you a big peak. Now, this peak is set by how much damping is in the filter. You can do a simple calculation of the Q of the circuit, and it's interesting in that Q is really the value of this peak divided by the value at the resonance, or the capacitive value, or the inductance. And it's interesting in that the Q of the circuit is equal to the peak impedance divided by the characteristic impedance. And the characteristic impedance is simply the square root of L over C. And another way to look at that, it is when the value of the capacitive reactance is equal to the inductive reactance. So here's a schematic of a simple way to damp an output filter. Here we have our input source, inductance between the source and the power supply. We have our capacitive filter cap here, and then we've inserted in parallel with it a damping resistor and then a damping capacitor. And we've set the value of the damping capacitor equal to N times the output filter capacitor. That'll help us normalize the circuit so we can develop a general case formula here. So the interesting thing is that there's an optimum value of the damping resistor once you've chosen the damping capacitor. And so what I've shown here on this set of curves is three different choices for the damping resistor. The case in green is the optimum case. If we have too small of a value of damping capacitor, we'll see that the peak comes up below this resonance and it can be significantly high. And in a limiting case, if you thought about just shorting out the damping capacitor and put 0 ohms in it for it, basically you have another high Q circuit, and its resonance is set by the output filter inductor and 1 plus N times the damping capacitor. On the other side, we'll see that the peak comes up also, and this corresponds to making the damping resistor too large. So, in the limiting case, if you opened up the damping resistor, you would have a circuit that's made up of the output filter inductor and just the output filter capacitor, and it's very high Q, and you would see the high Q that we see in this chart. Once again, once you've established your damping capacitor, there's an optimum damping resistor that goes along with it. And that's what this chart does for you. On the x-axis, we show the ratio of the output impedance of the filter divided by the characteristic impedance. And remember, the characteristic impedance is just the square root of L over C. And we've shown two curves here. The red curve is the value of the damping resistor with respect to the output filter characteristic impedance. And you can see that there's a blue curve here also. And the blue curve is the ratio of the damping capacitor to the output capacitor. So to use this curve, what you want to do is you want to normalize your power supply input impedance with respect to Z0. And so from our first chart, we saw that the power supply input impedance was equal to basically the operating point, that is the input voltage divided by the input current at low line. So you divide that value by the characteristic impedance of the filter, and you enter onto this curve. But you enter onto the curve so that you have a value of Z out max divided by Z less than this 1/2 Zn over Z out. And that pretty well guarantees the stability of your power supply. That says that the source impedance of your power system is less than 1/2 the power supply input impedance, and that guarantees stability. So you enter into this curve, and this will allow you to pick how large of a value of damping capacitor that you get by taking a look at the blue curve, or what the damping resistor is by looking at the left curve there. So thank you for your attention. For more power tips, take a look on the Power Management Design Line website, or take a look at EE Times and search on power tips, or you can click on the link to all articles in the description section of this video. Thanks.